Hello, my name is LEONIE Marie Diagne. Today I will be talking about my O-REU project, which is about molecular dynamics simulations of screw dislocations, mobility in copper. The sponsors of this project are the online O-REU program at Texas A&M University, the Department of Material Science and Engineering at Texas A&M University, and Texas A&M High Performance Research Computing. My mentors in this project are Dr. Michael G. Demkovich and Ta Dong. Screw dislocation is an important type of defect in crystalline materials. The screw dislocation structure figure on the right shows the top and bottom loading layers, and at the center is the screw dislocation. The application of shear stress on the top and bottom loading layers and in opposite directions causes the screw dislocation motion. Studying about screw dislocation is important because its mobility have a strong influence on material properties. So the goal of this research is to use molecular dynamics simulations to study the motion of copper screw dislocations at high strength rate deformation. Molecular dynamics simulation is used to study atomic dislocation. In this research, many software are used, such as Cisco AnyConnect, which is a secured VPN software used before connecting to the Texas A&M High Performance Research Computing, also known as HPRC. And it is an open source web platform through which users can access HPC clusters and services with a web browser. LAMMPS is the largest scale atomic molecular massively parallel simulator, and it is a molecular dynamics program. Last, O-REU, which is a visualization and analysis software for output data generated in molecular dynamics. Molecular dynamics simulation is done in 5 steps. First, a model of copper FCC structure is made with a screw dislocation inside. Then, shear stress at a certain velocity is applied on the top and bottom loading layers, and in opposite directions in order to make the dislocation move. In this example, the loading layer's velocity is equal to 5 meters per second. When the simulation runs, the files are saved in the HPRC system as dump files, and the time between 2 images is equal to 1 picosecond. In order to see the screw dislocation, the common neighbor analysis is done. Then, all FCC atoms are selected, then deleted. Last, the dislocation position in the X direction are found by opening every dump file and recording all the dislocation positions. Every time the screw dislocation passes over the right boundary, 1 LX length is added to get the X position, increasing continuously. The addition of LX, which is the box size parameter in the X direction, is because of periodic boundary condition. From the previous steps, the screw dislocation motion is recorded. In this example, the velocity of the loading layers is 5 meters per second. The first figure from the left shows the position of the screw dislocation at 1 picosecond, which is at the center of the boundary box. Then, at 27 picoseconds, the dislocation is at the right edge of the boundary box. The motion video shows the screw dislocation motion from 1 to 400 picoseconds at the same loading layer velocity as the figures. We notice that the screw dislocation moves from the center to the right, and once it hits the right edge of the boundary box, it goes back to the left and keeps moving to the right. As mentioned previously, the simulation is run over a period of 400 picoseconds, and the velocity of the loading layers is 5 meters per second. We notice that in this case, the dislocation position is increasing in function of time, and that the velocity is positive and not constant. The average velocity in this case is above 1400 meters per second. The same molecular dynamics simulation process is repeated for other loading layers velocity. Some are smaller than 5 meters per second, which are v equal to 1 and 3 meters per second, and others are greater than 5 meters per second, which are v equal to 6, 8, 10, and 20 meters per second. The first graph from the left depicts the dislocation velocity over time at loading layer velocity v equal to 1, 3, 5, and 10. We notice that all graphs are positive except the one of 10 meters per second. All graphs are not constant. The second graph shows the average dislocation velocity versus the loading layer velocity from 1 to 20 meters per second with the error bar. From this graph, we can conclude that the average dislocation velocity increases as the loading layer's velocity is increased. While repeating the simulations and reading the dislocation positions, we notice that when the loading layer's velocity is equal to 10 meters per second, the copper screw dislocation starts nucleating at 309 picoseconds, with a dislocation velocity around 2200 meters per second. We notice that once the dislocation reaches its critical velocity, it starts and continues to nucleate into new dislocations, even though the dislocation velocity changes over time. From the simulations, data, graphs, and figures, the findings of this research can be understood as the dislocation velocity increases when the loading layer velocity is increased. Also, once the copper screw dislocation has reached its critical dislocation velocity, around 2200 meters per second, new dislocation nucleate. This provides a good starting point for discussion and further research about what determines the critical velocity and how does screw dislocation nucleate. Thank you very much.